You can write that part of it. So you should know that all metals are solid at this point, except for mercury, which is a liquid. And this is on page 19, 19. So all metals are solid except for mercury, which is a liquid. You should know about the diatomic elements. The diatomic elements are all gases except bromine, which is a, what is bromine? Bromine is a liquid. And iodine is a solid. All the other nonmetals are solids, okay, other than those diatomics. All ionic compounds are solids. All ionic compounds are solids unless they are in solution. If they are in solution, they are aqueous. How can you tell that something is in solution? Well, number one, it will say it is in solution. Number two, you might be given molar. If it's molar, it has to be a solution. If it is the product of a reaction taking place in aqueous solution and is not a precipitate, we'll get to this part later, okay? A precipitate is a solid which forms when two solutions are mixed, and we'll talk more about that later. Okay, so we have a solution of zinc chloride is aqueous. 1 molar zinc chloride is aqueous. If I just write zinc chloride, that is a solid. A solution of zinc sulfate is aqueous. Solution of calcium chloride, aqueous. So we have two solutions, and they react to form zinc chloride and a precipitate of calcium sulfate. Well, when it says precipitate, a precipitate is a solid. Okay, and like I said, we'll learn more about that later. Since it does not say that zinc chloride is a precipitate, we can assume that it is aqueous. So for example, if we have zinc metal, what state is zinc metal? Zinc metal, that's not a state. It's a solid. Okay, what state is chlorine gas? It's a gas. It gives zinc chloride. Now, zinc chloride here, that's an ionic compound, and unless it says that it's a solution or it says molar, then you can assume that it is solid. Okay? These ones are tricky. So if you're learning it, you can go ahead and, figure it out. Small molecular compounds, H2O, NO2. You notice that the numbers are small, right? The subscripts, SO2, CO, NH3. It's not like XEF5 or C12H22O11, right? Those are not small compounds. Those are big compounds. Okay, all of the small molecular compounds are gases at room temperature, except water, which is a liquid. Acids are aqueous. By definition, if you have an acid, it is aqueous. If I give you hydrogen monochloride, then you can assume it is a gas. So you can, muck about with these if you want to, but it's not required. We're going to move on to section 6.2, and we're going to hang out with Tyler and learn about some types of reactions. Although, actually, do we even want to do that yet? Yeah, we do. Okay, here we go. Actually, before we start this,
let's talk about these 5.
Never mind. Let's just go ahead with it. So this is on page 21, I believe. 21.
Major types of chemical reactions. We'll look at examples of each and learn how to tell them apart so that you can look at a chemical reaction and classify it, figure out what type it is. The first reaction we're going to talk about is the synthesis reaction. These are sometimes called combination reactions. Now, synthesis is just a fancy word that means making, and that's exactly what happens in a synthesis reaction. A compound is made from simpler materials.
Okay, so you're going to fill that in on page 20. Synthesis, a compound, is made from simpler materials.
Here's an example. Carbon comes together with oxygen gas to make carbon dioxide, CO2. What we make in this reaction is more complex than the 2 simple things that we start with. Here's another example. We take sodium and chlorine gas, Cl2, and that makes sodium chloride, NaCl.
Do you notice how it's not NaCl2? Remember, you don't just toss the subscripts into the products. You have to just make the correct formula for Na, which is positive, and Cl, which is negative.
What we end up with is more complex than the simple things we started with. Now, a quick word about the equations that I'm using in this lesson. Some of these equations I'm going to be talking about, like this one right here, are unbalanced. So there might not be exactly the same number of atoms on both sides of the equation. Now, normally it's really important to balance equations, but when we're going to be learning about the different types of reactions, the balancing numbers can be a little bit distracting. So here, I just want you to focus on the elements and how they're rearranging or combining with each other in different ways. That being said, a synthesis reaction is one where we start with simple materials and put them together to make something more complex.
Are you guys familiar with the term synthesis in other contexts? Right? There's photosynthesis. You are making things. Absolutely. If you have a synthesizer, it makes music. Yes. I think in English, don't they give you like good marks if you do synthesis in your essay, right? You're putting ideas together, right? So you're taking things and putting them together. Simpler things come together to make something more complex.
If we want to represent a synthesis reaction more generally or more generically, we could say that it looks kind of like this. We have A and B combining to make AB. Here, A and B are different elements or they're different compounds coming together to make something more complex. So that's a synthesis reaction. Let's move on. A decomposition reaction is kind of the opposite of a synthesis reaction.
So a compound is broken down into simpler compounds or all the way down to the elements that make it up. And you can fill in the products. You'll notice that we have hydrogen and oxygen, which are diatomic elements. And so they have to, when they're on their own, be written as H2 and O2. Do we have to put a 2 beside the O in H2O? No, because it's part of a compound. They're only diatomic when they are on their own by themselves. Okay, so this hydrogen is by itself, so it's diatomic. This oxygen is by itself, so it's diatomic. It's not going to be diatomic in a compound because it gets its valence shell filled up in a different way. We will look at that more closely later.
In a synthesis reaction, we put things together. In a decomposition reaction, a compound is broken down into simpler compounds or all the way down to the elements that make it up. So in this example here, we have water, H2O, and it's breaking down into hydrogen and oxygen gas. These are the elements that make it up. Now, in a decomposition reaction, you don't have to break things down all the way down to their basic elements. You can also break them down just into simpler compounds. For example, here we have CaCO3, calcium carbonate, and that gets broken down to two simpler compounds, CaO and CO2. It's not like we're taking this and breaking it down into just calcium and just carbon and just oxygen, but still, because these are simpler compounds, it is also a decomposition reaction.
Now, along the way, you are going to have to predict the products of a synthesis reaction, of a decomposition reaction. You will be expected to be able to predict the top type where it breaks down into its two elements. Yes? You will not be expected to predict this bottom type here. Like, I don't expect you to know that carbonates, when they're heated, break down into the oxide and carbon dioxide. I don't expect you to know that, but you should recognize that this is decomposition, but you don't have to predict the products here. However, for the water breaking down, you should be able to predict the products. Just take the two elements, split them apart.
So if we wanted to come up with sort of a generalized way to write a decomposition reaction, we could write it like this. AB breaking apart into A plus B, where AB is some kind of compound, and A and B are simpler compounds or elements. Okay, combustion reactions. Combustion is basically a fancy word for burning. And when something burns, what happens is that a compound containing carbon and hydrogen, and sometimes oxygen, combines with oxygen gas to produce carbon dioxide and water.
Okay, so a compound containing which two elements? Carbon and hydrogen, sometimes oxygen. In fact, you might sometimes have nitrogen and sulfur, but we're just going to go with these ones for now. It combines with oxygen gas to produce carbon dioxide and water. When you start predicting the products of reactions, combustion is actually the easiest one to predict because the products are always CO2 and H2O, okay? Never anything else, unless we have, like, say, a sulfur in there or a nitrogen. We'll talk about those ones later, okay?
Here in my example, CH4, which is the chemical formula for methane, that's a type of natural gas, combines with oxygen, and it forms carbon dioxide and water, H2O. Now, we can start with different things in a combustion reaction, and as it says here, the compound usually contains carbon and hydrogen. So here is another example of a combustion reaction. This one starts with C3H8, which is the chemical formula for propane, another type of natural gas. And just like with this reaction, we combine C3H8 with O2, and this gives us carbon dioxide and water.
Can you predict the products for the next reaction? CO2 and H2O. Shocking, right?
So these two reactions are essentially identical, except for the number of carbons and hydrogens in the compound that we start with. It turns out that a lot of things that we burn, like natural gas, diesel, gasoline, are really, really similar, and they only really differ in the number of carbons and hydrogens that are in the molecules that make them up. So combustion reactions for a wide variety of compounds look pretty similar. Now, as this definition says, sometimes we have oxygen in the compound that we're burning. Here is one example of a combustion reaction that has oxygen in it. This is the chemical formula for ethanol or ethyl alcohol, and you can see that just like these, it has lots of carbons and hydrogens, except it also has oxygen as well. But that's no big deal because it combusts just like the other two by combining with oxygen and making CO2 and H2O. So if we wanted to come up with a general way to write the formula for a combustion reaction, it might look a little bit like this. we start out with something that has carbon and hydrogen in it. And we can have different numbers of carbons and hydrogens. So that's why I put this X and Y here, because the number of carbons and hydrogens varies, and it doesn't really matter either. Sometimes the compound has oxygen in it, which is why I put the oxygen here in parentheses. We take this compound, it combines with oxygen, and it produces carbon dioxide and water. So this here is the generic general equation for a combustion reaction. Single replacement reactions break my heart, and in a minute you'll see why. So in a single replacement reaction, what happens is that one element that starts out by itself replaces another element in a compound, kicking it out.
So actually, I've got a question for you here. What type of element is iron? What type of element?
Metal.
It is a metal. And what is this compound made of? It is made of copper, which is a metal, and chloride, which is a non-metal. What do you think Fe will replace? Will it replace the metal or the non-metal? Metals replace metals. Okay?
And here's an example to show you what I mean. We start out with iron, Fe, which is this element that's by itself. And iron combines with CuCl2, which is copper chloride. Okay, so copper and chloride are paired up here. But what happens is iron kicks out the copper, the Cu. So the Cu ends up by itself, and the Fe, the iron, takes the place of that copper. So now the iron and the Cl, they are now paired up.
Now, just in case you're wondering, you're like, hey, maybe you're thinking iron could be 3+ or iron could be 2+. How did you know that it was 2+? When we're predicting products, we generally go with the rule that if you have a multivalent metal and you aren't told what charge it will form, afterwards you can assume that it's the number 2. So if you're like, I don't know what the charge of iron is, just assume that its charge is 2+. Okay? You might be right, you might be wrong, but we're going to just make that because it makes predicting products a lot easier. Otherwise, you have to know a lot more chemistry than you do right now.
Now, I like to use a dance analogy to explain this, and it reminds me of something that happened all the time in high school. Here's what's going on. We have a dancing couple, the purple and the green, and they're so happy dancing together, or at least the purple guy is pretty happy dancing. And then red comes along. And red is like, hey, purple, I'm so much cooler. Get out of the way. I want to dance with green. And so poor purple gets booted out and red ends up dancing with green. Purple ends up all by himself, standing up against the wall, pretending to text, pretending to play a game on his cell phone, but you know, he's really actually sad because he's just been booted from this dancing couple.
Okay, now we're going to take 1 second here and go to this thing because obviously you don't have a color version, so I put little hats on the metals. The metals have hats. Okay? And the nonmetals have no hats. Now, when it comes to quiz or test time, you are not going to be expected to do anything other than recognize this as single replacement. But while you are learning about predicting products and things like that, you're going to take a look at this and you're going to say, this is a single replacement metal because the metal is replacing the metal. So you can call it an SR for single replacement and then an M. Okay? Now, later on, we're going to see, and Tyler does not do one like this, so maybe we're not going to see this one. We can have a single replacement non-metal, and you'll notice here that we have, what have I done? I need to change this so that the hats, here the hats represent the non-metal. I need to change this. So here the hats is the nonmetal. Oh, I think I gave it to them so you could see the difference between who got replaced and who didn't. So I need to figure this all out. Okay, so in this case, the hats equal the nonmetal, and so the nonmetal kicks the nonmetal out. So for example, if you have Cl2 as your element, it is a nonmetal. It's going to replace Br, which is the nonmetal in the compound. And do you see how Cl2 is one of our diatomic elements. It is, yeah. It's diatomic on its own. But in a compound, it's not diatomic. And that's because Cl2 how many valence electrons does chlorine have? Everyone, how many valence electrons does chlorine have? Group 17. 1? How many valence electrons? Not what's its charge, how many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. Is that a stable atom? No. So what it needs when it's just chlorine on its own is it needs another chlorine to help fill its shell so that they are both full and stable. But if we have sodium chloride, remember Na? Na is in column 1. How many valence electrons does it have? Column 1. 1. Chloride has 1, 2, 3, 4, 5, 6, 7. How do these both become stable? I have a metal and a nonmetal. Do they share? Do metals and nonmetals share their electrons? No. What does sodium do with its electron? It gives it away. So you end up with Na with no electrons in its valence shell with a positive charge, and Cl with that extra electron from chlorine with a negative charge. Okay, so chlorine does not need a little buddy in an ionic compound because it gets its electrons from the metal. Okay, it needs a little buddy when it's just chlorine because otherwise its shell is not full. All right, let's bop back to Tyler here.
So you'll see that this is exactly what's going on in the single replacement reaction, right? Fe, iron, is like red here. Coming up to a dancing couple of Cu and Cl, it boots out Cu, Cu ends up by itself, and then red, iron, takes the place that Cu had, and iron ends up paired with Cl. Here's one more example of a single replacement reaction. You can see how this works. Cu in this case is the red character, and Cu goes to a dancing couple of Ag, silver, and nitrate, AgNO3. Cu boots out Ag, so Ag ends up by itself, and Cu takes Ag's place by pairing up with NO3. So that is how a single replacement reaction happens.
And you'll notice that copper is one of the multivalent metals, and so what charge did we give it? 2.
And a generalized reaction for that would look like A, which is the element that starts out by itself, plus Bc, that's the dancing couple, And then that gives us B by itself, which is this element that got booted out, and then A and C ending up paired together. So that's a single replacement reaction. So finally, here's the double replacement reaction. Now I should mention that single and double replacement reactions are sometimes also called single displacement and double displacement, just in case your teacher or textbook uses a different term for them.
You won't hear me use displacement, but you might at university. Sometimes if you go somewhere, just depending on regional usage, they might call it single displacement or double displacement.
Okay, so double replacement reactions are not nearly as heartbreaking as single replacement reactions. Here's why. Because in a double replacement reaction, what happens is the positive and negative ions in two compounds just switch places. Nobody gets kicked out in a double replacement reaction. In a double replacement reaction, it's just like you have two different pairs of dancing couples, and the red, which used to be with the gray, ends up with the green. And the purple, which used to be with the green, ends up with the gray. Nobody gets kicked out. Nobody's sad up against the wall with their cell phones. We're just switching dancing partners. So here is a chemical equation that shows a double replacement reaction. We start out with Ba and Cl together, and then Na and SO4 together, and they just switch places. So Ba ends up with SO4, there it is, and Na ends up with Cl. There it is right there. All of these compounds are ionic, which means that we can break them down into the positive and negative ions that they're made up of. So here, the positive ions are in purple, and the negative ions are in green. And as you can see, the positive and the negative just switch places. So Ba2+ and Cl- were initially paired up. But then Ba goes and it gets switched. It finds a new dancing partner. It has to find the other negative ion, right? So the other negative ion here is SO4 2-. So Ba2+ and SO4 2- end up together, making BaSO4. And then sodium, Na1+, has to find the other negative ion, which here is Cl-, and they end up paired up over here. Na1+ and Cl1- making NaCl.
Now, just before we carry on, one of the most common mistakes that people make is that they'll be like, okay, Ba goes with SO4, BaSO4. Cl goes with Na, ClNa. Can you imagine writing sodium chloride as ClNa? It happens. Don't do it. Okay, make sure which ion always goes first in the compound. The positive ion. And in fact, one of the ways to make predicting these products easy is by writing out all your ions like this, and you take your outside ion, so the ones on the outside, the Ba and the SO4, and you pair them up, and you go forwards, Ba, SO4, and then you take your inside ions and you go backwards, Na, Cl. Okay, and when we actually get into predicting that, we'll draw little arrows and things. That's just giving you an idea of how they go.
Has to find the other negative ion, which here is Cl-, and they end up paired up over here. Na1+ and Cl1- making NaCl. Here's another example of a double replacement reaction, okay? I'll break this down into its ions right away, and we get this.
And you'll notice outside ion, K and NO3. Makes NO3. Inside ions, Ag, and remember we go backwards with our inside ions, AgBr. AgBr.
We start with K+ and Br- paired together, and Ag1+ and NO3 paired together, and then they just switch the positive and negative. So K+ goes and finds the other negative ion, which here is NO3 K+ and NO3 end up together, and Ag1+, silver, looks for the other negative ion, which is Br1-, and Ag1+ and Br1- end up paired up together, making AgBr. So that is a double replacement reaction, and if we wanted to come up with a general or generic way to explain it, we could use this reaction here, where we have Ab where A and B are paired up, plus CD, where C and D are paired up. And then they switch partners to give us AD and BC. So that is a double replacement reaction. So these are our 5 major types of chemical reactions.
Oh, I fixed it.
In synthesis,
okay.
Simple things combine together to make something more complex. In decomposition, something complex breaks apart into simpler pieces. In combustion, a compound that contains carbon, hydrogen, and sometimes oxygen comes together with oxygen gas to make carbon dioxide and water. Single replacement and double replacement are our 2 dance floor reactions.
Now, before we carry on with that, I want you to tell me what is wrong with what Tyler has written for double replacement here. Right? Positive ion goes with negative ion, and the positive ion goes first. Here, positive ion goes with negative ion. The positive ion should go first. So don't make that mistake. Okay, and I think that's actually basically it. We have one more type that Tyler does not talk about. Do you guys know what it is? Neutralization. And neutralization is just a special type of double replacement, but if you call it double replacement, you will not get credit for recognizing the reaction, because you need to know, how do you recognize that something is an acid? Acid has an H at the start. So we have H something. How do you recognize if you have a base? You have something, and then you have an OH at the end. So that's what you're looking for to say, do I have a neutralization? Now, just like the double replacement, you can say this is an H plus ion, this is an X minus ion. This is a B plus ion, this is an OH minus ion. What do we get if we combine our outside ions? H plus and OH minus. We get HOH, which is actually H2O. Okay? And actually, when you're doing neutralizations, if you have not yet balanced them, if you find balancing neutralization difficult, I actually recommend writing water as HOH and balancing the H's and OH's separately. Now, we combine our inside ions, so we go backwards. The B gets together with the X, and so we get BX as our salt. So we have an acid plus a base gives a salt plus water. That's a neutralization reaction. Acid plus base gives salt plus water. And I'm going to give you guys about 10 minutes to work on pages 23 to 24. And all it is recognizing what the type of reaction is. Okay? So work on pages 23 to 24. And then we're going to move on to some balancing stuff. Yeah, let's grab that. Let's grab that for you. Yeah. Oh, you actually look like some snow a little bit. Well, to be honest, you can write this because we're really I'm also very so these are the same. Ready? What buttons? Yes. No, it's not. It's not. Guys, I'm like, just, you know, 5-year-old, like this, right? I'm in farm parent. Yes. Yeah. Right? Yeah. Oh, the answer is wrong. Yeah. Yeah. Now, I wonder if I got enough of those. Do you guys like your color version of all the types of reactions?
Yes.
Okay, there we go. There's 2 sides to it. You can pick which one you like. You can flip to the other side and see if you like that one better. So now you won't have to flip at all because you've got brown. I don't know where else. Did I miss anybody with this? I think which one you like better. If you are finished and you would like to work ahead, you can start looking at pages 27, but we'll be going through it together in another minute or two anyway, so. Yes. Is it possible that you lost it outside as well? Oh, I think I have it in my bag. Somebody found it on the ground yesterday. And then I had things on my desk, and I just needed to clear it up, so I threw everything in my bag. Let's see where I put it. Dear. That looks promising. No, that's not it. It's okay. We'll just grab you a new answer. Okay, I've got lots. Okay, folks, if you are not finished that, it will be something you can finish after your test tomorrow. Okay. And we are on page 25. This just gives you some basic tips about balancing, okay? I have better tips for you coming later, but you can always refer back to this page. There is also a link to a playlist of balancing from easiest to hardest equations, okay? So these videos are full of awesome tips like balance the hydrogen and oxygen last. If a polyatomic ion appears on both sides, treat it as a unit. Don't try and balance the oxygen separate from the P's when you got phosphorus. Treat it as a group. Assume you have one of the most complicated compound and go from there. And there is also how to balance with fractions. I've made a way to look at that. And a few other things. Make sure that you are changing the coefficients, not the subscripts. Again, treat polyatomic ions as a unit. We mentioned this one yesterday, the LCM, the lowest common multiple. It is your friend. So if you have 2 of something and you have 3 of something, you're going to try and make sure that you have 6 of that particular thing, yes? There's some strategies about combustion that there's 2 different strategies. You can use halves to get an odd number of oxygens, and I will show you how to do that. The other strategy is to multiply the hydrocarbon by 2, if you prefer, and then you balance it and you reduce to the lowest terms. What on earth does that say? Reduce to the lowest terms. Get rid of that. I need to fix that. Okay, and then neutralization and single replacement. In both of them, it helps to write H2O as H and OH and balance the H OH minus as a unit. Another generic thing, balance the greatest number of atoms first, and then do other elements, then do hydrogen and oxygen. And if you have any lone elements like Cl2, Fe, O2, N2, Cu, you will balance those lone elements last. Finally, if you have halves, you're going to multiply your equation by 2, check the number of atoms by counting, and reduce to lowest terms. There's a whole bunch of tips and tricks expanded here. You can read through them. I'm not going to read through them. We're going to move ahead to page 27. So strategy number 1 is to use a chart. We started doing this last day, and what I mean by using a chart, and you can follow along or you can write it along with me if you prefer. You get yourself some paper, but every step is shown for you on the page. What you would do is you would say, I have iron and oxygen and carbon. Those are my 3 elements. And on the right-hand side, I have iron and oxygen and carbon. And you write down how many you have of each. How many irons on the left? Everyone, how many irons on the left? 2. How many oxygen on the left? 3. How many carbon on the left? 1. How many iron on the right? 1. How many carbon on the right? Sorry, oxygen on the right. I should have gone in order. 2. And then carbon is 1. Now, we have a 3 and a 2. So that's a good place to start. Yes? What should we multiply by to fix that 3 and that 2?
6.
We need it to equal 6. So what are we going to put in front of the Fe2O3? We're going to put a 2. And what are we going to put in front of the CO2? We're going to put a 3. And now we have to make all our changes to our numbers. So now we look and we say we now have 4 iron. So you have to cross out the 2 and write a 4. We also have 2 times 3 is 6 oxygen. So make sure you keep updating your chart every time you add coefficients. We have 3 times 1 is 3 carbon. So we update our chart. And 3 times 2 is 6 oxygen. So oxygen is good. Now we need to balance iron. Thank you. How many iron on the left? 4. So we need to put on the right, we need to put a coefficient of 4. And now we update our chart to say 4 iron. And we have 3 carbon on the right, so we need to put a coefficient of 3 on the left, which gives us 3. So now we can say I've got 4, 4, 6, 6, 3, 3. Everything is good. Is good? Okay. Strategy number 2, even and odd atoms. This is basically the LCM rule again. If you have an even number, it doesn't matter if it's 2 and 3 or if it's 5 and 4 or whatever. If you have even and odd, you're going to go for the lowest common multiple. And that is what we just did there. So we had our odd and our even. Okay. Now, how about you guys try numbers 1, 2, 3? It's up to you whether you keep the little chart or not, but it can be helpful. You're also going to recognize the reaction type. And remember, you've got your reaction types on that little handout, so you're going to fill that in. So you can do questions 1 through 4. There. Not here. You can tell them she's not attending. Okay. You're good. Yeah. Okay. Honestly. Yeah, I usually do that very first. But I didn't get it today, so I gotta look at it. Because there was the cheddar. Sweet what you don't want to see. If you get stuck on anything, let me know. If you have any questions, check them with your answer key. Oh, yeah, so from Tuesday to one. Yeah. Exactly. Yeah. Right now,
So what else is it? Right, sorry, I'll read it. There you go, that's gonna be the 6 ones. Two here, and one here. Which one do you consider 6? Look at that here, right? Right here. Times now, this is the balance, right? And you can check the night with them. We want nothing. Yeah. That's for her. Yeah, okay, so are we going to a bit about it? Right. If you're feeling it, it's over there, yeah, it's good. Absolutely. Yeah. So here it is, you start by writing that, you have the whole page in one day. One, not quite one. That's what they know what it's. Yeah, so one day, or you have number of CLs on each side. Yeah. And then those on each side. Now you're gonna look at, okay, I have an odd number of CLs. And it's even number of rows. You will work on the phone. Okay, so on this side, I need to multiply this by this. Yeah. So you'll put it here. Yeah. Yes, exactly. And then you're gonna update your little chart size. That way you're saying, okay, so on this side, now you're gonna update this one. You guys have 6 options. Now, you say, oh, hang on, I got 2 Ks, 2 PLs. Here I need to kind of do 4. So I'm gonna put that. Yeah. I just can't put on. Yeah, no, that's exactly. Okay. Okay, good stuff. Good? Yeah. And we good? You still don't know how to do it. What's causing you the problem? You'll get used to it. Okay? It looks like it have ours. I have policy.
Oh, I guess you're.
No, I got yours. NAs. All right.
Yeah, you just saw my.
Oh, it looks like you know what you're doing, you just need like more confidence. Is that right? Okay, cool. Did you get stuck? Or did you just start moving off? Okay. Alright. Okay. So what you do is start creating a so here you have 1 point, 1 CL. Okay. Here, 1 K. That's 1 CL. We have 2 O's. So what do you need to do this? Not have the same number on each side. O's. So you have to bring 2. Yeah. So what you're gonna do is you start right down here. Ready times 3. Yeah. Yeah, you get it straight on here, so that's a 3, and then here you go. 2, so now we have 6 and 6. We need to change anything else that also runs. How do we sure thing? Yeah.
What's it?
Okay, let's see, now you've got 2 and 2 and 2. Yeah. 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 Okay. Oh, no, it's the one crossed out. Oh my God, what's wrong with you? Oh. Okay, so what we're gonna do is we're gonna say we started with 4 and 1 and 10, 5. Oh no, 4, because I can't count apparently. Actually, we have 11 oxygens over here. Oh, yeah. 11. Okay. And we have 2 hydrogens and we have 3 hydrogens. Okay, so what I would do, just erase all of that, okay, is I would say I have an odd number and an even number and an odd number. I might deal with those ones first. Let's just try that, okay? So let's multiply this by 3. Update your chart here so you can say now I have 10 plus 3 is 13. Okay, and you have 2 becomes 6. Okay, and then this one you had a 2 in front of there, so don't get rid of that just yet. Okay, so now we have 6. Okay, now this is where it becomes a little bit like, ooh, right? This is one where you just sort of have to go a little bit into it, okay? And you have to say, well, the problem is that this being a 3 messes it up because I have an odd number of oxygens. I would like to have an even number of oxygens. So why don't I multiply that by 2 and why don't I multiply that by 2? 4 and 6. So now I'm going to do numbers. See how that went. So is this plus 6 with me? Yes. No, 10 plus 6. Oh. Yeah. That one I don't know. 4 times 4 is 60. Okay, and now you have to update your phosphorus. You now have 4 phosphorus. Yeah. Okay. Most of them aren't going to be like this, but you'll kind of get the hang of it along the way. Okay.
So what's your homework? Study for your mole test tomorrow. Okay? After your test tomorrow, it'll just be finishing off like what you didn't get done here or on the other page, okay? And then we'll move along shortly. Balancing combustion reactions with fractions, so looking forward to that.
Oh, yeah, if you want to, sure.
Yeah, come help yourself. We'll get you. Articles. Yeah, sure.
Thank you.
There we go.
Thank you.
Yeah. You're welcome. Oh, yes, this is the same. There's one of those, and then one of those.
Can I get a mole, like to practice, like a quiz,
Yes.
if that makes sense?
Yes. There we go, and particles, moles, mass. Yeah, that's the one. Yeah. There you go. I have like 1 million copies of the first quiz if you'd like it for practice. So if anyone would like the first quiz for practice, I'll just leave it there. The second quiz, I might even have some of those. You might need to wait for a printout though, if I run out.
For tomorrow.
Okay. And this is the second quiz. I'll print out a few more of those as well.